Next up over here, next talk will be in English, and we have with us Adrian Herrmann. Adrian joined the Qt for Python team in July 2022, drawn by the unique challenge of combining the worlds of Python and C++, a journey that has sometimes taken him into fascinating depths of the Python language and the CPython interpreter. Previously, he worked in the embedded and automotive industries and graduated at the Freie Universität Berlin. And Adrian today is going to talk to us about asynchronous programming with AsyncIO and Qt. Big applause for Adrian.
All right, can you hear me? Okay. My first time speaking at a conference. Thank you for showing up, and also thanks, Alejandro, for the introduction. So I guess I'm Adrian. I work at the Qt company, as he said. I work in the Qt for Python team specifically. Today I'm going to talk about asynchronous programming with AsyncIO and Qt, and more specifically, I'm going to talk about implementing AsyncIO's event loop interface for Qt. So first of all, I'm going to ask you for a quick show of hands. Who here has heard about or used AsyncIO? Quite a few, okay, that's good. And who here has used or heard about Qt, spelled Qt? Also quite a few, that's pretty cool. All right, so I'm going to dive straight in. I'm going to start talking about what is GUI programming and event loops. How do we use event loops for GUI programming? So GUI programming is fundamentally event-driven, right? So we've got mouse clicks, mouse movements, or we type in something with a keyboard. Each of these is an event that our GUI program needs to handle. If it doesn't handle this event, it's going to freeze. The way it works on a technical level is all these events are always triggered by peripherals, or usually triggered by peripherals. They interrupt the CPU, the operating system then handles this interrupt, and the way it does this is it passes an event onto the program. So it tells the program, like it figures out this program window was open, we clicked a button, and it tells the program, this button was clicked, do something with it. And the program needs to handle this event. So it's fundamentally event-driven, where you've got a GUI. This program needs to continuously check for new events, and this is what we call an event loop. So every platform that offers some graphical capability has some form of event loop implemented that graphical programs can then leverage. The thing about event loops is they're not just good for GUIs, so they enable other things. And specifically, what you can do with them, you can program asynchronously. You can create an asynchronous event-driven program that is one single threaded. So that's the crucial point here. It runs on one single thread. We can, of course, just create multiple threads in one program and have asynchronicity that way. But with an event loop, we can do this with just one single thread, which might be useful or more scalable in many cases. The basic idea is that we have tasks that may block, and we want to move on to different tasks while these tasks block. So a task like this would be not CPU-bound, but an I/O-bound task. Imagine you've got like storage device that we need to read from, or network data that we're waiting for. We're going to wait. It's going to block because we need to wait for this peripheral device. And while we block, we can move on to a different task, right? We don't want to waste our CPU cycle while we wait for some I/O device. So we're going to move on to the next task. That's the idea. So this is cooperative multitasking on an application level. If you think about multitasking, I think the first thing that will come to mind is preemptive multitasking on an operating system level through threading different processes. You've got different processes that the operating system preempts. That's what we think about when we think about multitasking today, mostly. But there's other forms, and there's cooperative multitasking. This on an application level, so it's not the operating system. It's one single application. And the tasks need to cooperate to enable the multitasking, right? A task needs to yield at an appropriate moment so that another task can run. Event loop-based programming is based on callbacks. Now, if you've ever tried to write a program that's based on callbacks, you might have run into something that people like to call callback hell, where you've got many callbacks nested within each other. It's not always intuitive. It can get pretty ugly. And so we try to abstract this, and we can achieve this through a combination of a language and a framework. On Python, we've got something called coroutines. Maybe you've heard about those. especially if you know AsyncIO, you've probably heard about those. So we've got coroutines, we've got the async and await keywords in Python. You may have seen these even if you didn't understand what they mean. Async is something we can put in front of a def. So we define a function with an async, we say async def, and that's instead of a function, that's going to define a coroutine. You can picture, for the purpose of this talk, maybe the coroutine is simply an asynchronous function. If you know what a generator is, if you heard of generators, then this is going to ring a bell, because coroutines work very similar. The await keyword inside a coroutine tells us that at this point we can yield the execution and we can resume the execution when the result of an operation has finished. So in practice, it looks like this, a very simple example. We've got the async def. This is a coroutine do something. We know it's a coroutine because of async, the async keyword. Here we await something else, and this could block. And at this point, we're not going to block here. We're going to yield the execution of this coroutine. So while we wait for this to finish, we can move on to a different task. At some point, this will finish. We can come back here, and then we get the result from the await, and we can work with that, print it, whatever. So that's the basic idea of the async await keywords. This is how they interact. I want to come back to GUI frameworks for a moment. I've talked about the event loop. If you use a GUI framework, you're not going to interact with the event loop much. The idea is that you want to abstract this, right? You don't want to deal with the minutiae of this. You don't want to do all the stuff manually. You want to abstract this. Maybe you've got a function that to start the event loop and to stop the event loop, but that might be it. What GUI framework also wants to do for you is you don't want to write a GUI hand by hand, pixel by pixel, of course. Nobody wants to do that. So a framework is going to provide some form of UI building blocks. This could be widgets. You've got widget-based frameworks. Let's say you've got a widget for a text box, a widget for a button, widget for a table, whatever. And we can arrange those. Or maybe you've got a markup language that allows us to define the user interface and callbacks in markup language. In Python, there are a few household names. If you've ever tried to write a GUI program in Python, you've probably run across one of these. But I'd like to introduce another framework that you can use in Python, and that is the Qt framework. So the Qt framework, spelled Qt, is a GUI-oriented cross-platform framework. It's not only for GUI, there are some APIs for other stuff, but GUI is the main focus. There are a few big names that you might know: VLC, Media Player, Autodesk, Maya, Telegram. These are just a few examples of programs that use Qt. They're open source and commercial licenses. It targets all desktop platforms and a few more. And it's actually a series of native libraries for C++ programming. So this is still a Python conference, not a C++ conference. So the cool thing is that you can use these with Python as well. You may have heard of bindings in Python. A binding in Python, remember in Python we've got the interpreter that is written, for example, in C, like CPython. A binding allows us to have a link between a Python code and some native code. So the Python interpreter can load some library with native code, and then the Python code can call code from this native library. And we achieve this through bindings. There is an official collection of bindings that's called PySide, and this is the Qt for Python project. So you can use Qt with Python. A few of you might have heard of PyQt, and maybe a bit confused right now. PyQt is from the idea, the idea is the same thing. It's also a collection of bindings, but it's not from the Qt company. It's an unofficial series of bindings. And there's a bit more to Qt for Python than just the bindings. But if you've heard of PyQt, if you know what PyQt is, you know basically what PySide is, because the idea is the same. Bindings between Python and the native libraries. The API is almost the same. So the idea is to use Qt on Python, but you don't make any compromises. You've got the full power of the entire API, of the entire framework. It's the same binary code that's executed after all. You just got some syntactic sugars and pizzas so that the programming is more Pythonic and better in every way if you're a Python programmer. If you want to install PySide, it's as simple as running a pip command. So Qt is based on an event loop by nature of being a GUI framework. We start Qt programs by calling exec function on this event loop. Remember I said, even with framework, we might have a function to start the event loop. This function is going to block as long as a loop is running. And at the end, we need to unblock this. We do this by calling an exit function from within the event loop. There are no coroutines in Qt. We've got a mechanism that's called signals and slots. You can picture these as slots are basically callbacks. So we do an object can emit a signal, it does not know who's going to handle the signal. This signal can then be, we can register a slot to the signal, and the slot is basically like a callback. But through this mechanism, we have encapsulation between objects, and we've got these signals, but we don't have coroutines. So this is what a Qt for Python program would look like, a very simple one. So we've got, here we've got like this slot decorator tells us that this function is going to be slot, like a callback basically, right? We've got here, we've got Q application, window widget, button widget, and we've got this signal. The button class has a clicked signal. We connect it to the slot so that when we click the button, this slot is going to be executed. We also got this window.show, and at this point, nothing's going to be visible yet, because remember, we have an event loop. Only when we call app.exec, we start the event loop. Before that, we've only enqueued events into the event loop. So at this point, we can start the application, and what it's going to do is, we've got the button with the label that says hello. When we click it, we're going to change the label of the button. So it's pretty simple. It looks like this. You click, and we change the label. It's pretty much as simple as it gets. This is a very simple Qt program. And now, I'd like to talk about the other big part of my talk, which is AsyncIO, which a few of you have already used, apparently. So you will know that AsyncIO is a library to write concurrent code using the async await syntax. That's their own description on the documentation, and it's on point. It's part of this Python standard library. It's also a foundation of a number of other frameworks. Maybe you've heard about a few of these or even used them, and you didn't know that they were based on AsyncIO. And their names kind of give away what you'd use AsyncIO for. You see IOMCs and HTTP, right? So it's IO related. And curiously, I learned recently that Telegram Discord bots are also written with AsyncIO, which is pretty nice. When would you use AsyncIO? I think you can get different answers to this. The answer that I would give is you might be interested in AsyncIO when you've got a program that needs to handle many I/O operations from many sources. Let's picture a server that has hundreds of incoming client connections. Sure, you can just spawn hundreds of threads, but at some point that might not scale that well. And why have hundreds of threads if you can just run one event loop where we can handle all these clients in one single thread, right? So this is one example where we might use AsyncIO. So we've introduced Qt and we've introduced AsyncIO. Now the question is, how can we bring these disparate concepts together? What's this all about? Remember, Qt is a framework for GUI-focused applications. We don't have coroutines, we have the signal slot mechanism. In AsyncIO, we do have async await syntax instead of callbacks. We have coroutines. It's a framework for I/O applications, and we've got integration with other Python libraries and async frameworks. And what do they have in common? They're both based on an event loop. So that gets you thinking, maybe we can do something based on that. Maybe we can write a program that uses Qt and AsyncIO together. How could we do this? Maybe naive idea, run both event loops together, like at the same time within each other. Well, no, that's not going to work, as Dali shows us here with his cartoon impression. No. But maybe they could share an event loop, right? Because we've already got this bunch of stupid code that's checking all the time, is there a new event? How do I handle this? It's doing this all the time. We've already got this, so why not reuse it for both frameworks? Maybe this event loop can take care of dispatching events to the corresponding framework, and then we can use both together. So I'm not the first person to ask this question. In fact, this question has been baked into the design of AsyncIO from the start. And that's why there are abstract classes that you can implement to write your own custom event loop. So the idea is that you expose the same API to users. It's the same API. You write an AsyncIO program that you would always do, but you transparently replace the event loop with your own custom implementation. And ideally, users would only notice because something got better or you enabled new features, but nothing would get worse. It's supposed to be transparent replacement. So our goal here, what I've been working on lately, and also what this talk is about, is let's try to bring these two frameworks together, AsyncIO and Qt. Let's try to bring it together so we can mix and match Qt and AsyncIO code. We could even use the Qt library with async in a way which is blend everything together into a bundle of happiness. So what we need to do to achieve this is, well, we've got this abstract class. Let's implement it, right? Let's implement the AsyncIO event loop with Qt's event loop so that we can run AsyncIO programs with the Qt event loop as the base. And then we can also run Qt code. So we could have code from both frameworks together and achieve nirvana. So I'm going to talk about this API. That's what this rest of the talk is going to be about. And in my opinion, you can divide the API into two levels. The first level is for fundamental infrastructure. So these are classes that you need to have if you want to run an event loop. If you want to run asynchronous stuff, you need these classes. I'm going to talk about these. You need these classes, otherwise nothing's going to work. This fundamental infrastructure. And then we've got a user-facing API. If you want to write a program that does anything actually useful with AsyncIO, you're going to want to use this part of the API. Here we've got like network stuff and stuff for also like sockets and signal sub-processes. This is what we want to use when we write a program. But the meat of this talk is going to be the infrastructure, because without this infrastructure, nothing goes. It's the fundamentals. We need this to do anything at all. So this is what I've been working on. And so I'm going to introduce these classes now. I'm going to start with a class that is called future. So a future, maybe you've heard of futures if you've done asynchronous programming. The idea of a future is it's an object that can be awaited. So when you await a future inside a coroutine, remember the await keyword? What's going to happen is that this coroutine is going to yield. We return to the event loop and we move on to a different task. The execution is going to resume when the result of this asynchronous operation is available. The future represents some operation that we want to wait on, okay? And when this operation is finished, we can set the result of the future, and that's when we can resume the execution of the coroutine. Or maybe you can also get an exception or cancelled, but this is the point where we can resume, when something happened to the future, when we got a result. And this result is then returned by the await statement. The future only manages a result. The future does not execute any code per se. I mean, it's only supposed to manage a result to tell the event loop, okay, you can continue here. You can resume the execution at this point. So what you see here is a very simple example from AsyncIO's documentation. What you see here is we ask the event, the way you use a future, you might want to use a future, you can ask the event loop to create a future object for you. We pass this object onto this coroutine as an argument. As you can see, this coroutine is going to do the sleep with a delay, okay? And when it's finished, it's going to set the result of this future to tell us that this operation finished. And this is what happens down here. We got this await future. This is going to yield until the result of this future is set, and at that point we can resume. So what is this program going to do? We print hello. We await the future that we passed onto this coroutine. And this coroutine is going to sleep for a delay of 1 second, and then it's going to return this world value, and we're going to print the value set inside the future, okay? So await future will return this value, which is world. So what you should see when we run this code is we print hello, we wait for 1 second, and then we print world. And this is indeed what happens, hello and world. So now moving on to the next class, a very important class, the task. So tasks are slightly confusing because they're considered future-like objects. You find this in documentation quite often. And what does this mean? They have a very similar API, but tasks are much more not much more important, but they do something else because they run a coroutine. Remember, future only manages a result. A task is what actually is going to run the code of your coroutine. It's going to be run from within this task. So in a way, in my opinion, tasks are the building blocks of asynchronous execution, because a task will run, suspend, or resume a coroutine. And remember, I talked about the cooperative multitasking, right? So we switch between tasks. We always run one task at a time, and these are the tasks that we run. The task class represents one task that we run inside the event loop, one at a time. It runs a coroutine. It runs a coroutine until it either finishes or raises some exception or returns a future. If our coroutine returns a future, the task is going to await its completion. And that's the signal for the event loop to say, okay, here we wait, we yield the execution of this task, we can move on to another task. At some point, our future will have a result set. And at this point, we know, okay, we can come back and we can come back to this task and resume the execution. And that is, that is the cooperative multitasking. So here, you saw early AsyncIO.run, maybe you saw that I called this function. If you use AsyncIO, you probably know that this is how you start a synchronous program. You've got some main coroutine that you pass as an argument to AsyncIO.run. And this is the code of AsyncIO.run. the relevant part here is down here. You see, we've got the coroutine as argument, and we create a task for this coroutine. So that's when we start a synchronous program with this coroutine, we create a task for this coroutine. This is the implementation, the constructor of my task implementation. And I'd like to point out this line. This line has this mysterious call to call zoom function, mysterious step function, and a mysterious handle object. And these are crucial to the event loop, and I'm going to address these now, starting with the step function. We want to call inside the event loop this step function, okay? And the step function, this is not part of the API per se, it's an implementation detail, but this is how I decided to go, and also how AsyncIO decided to go. Remember I said the coroutine runs until it throws an exception or returns a future or until it's finished, and that's what you can see here. So corout.send is going to run the coroutine until it yields. And at that point, it might return a result. It might return a future, for example, or there might be an exception. One type of exception is going to tell us that we are finished, the coroutine finished, with a valid result. Another type of exception is going to tell us that the coroutine was cancelled. Another type might tell us that we were done with some other type of exception. And at the end, what we want to do is, like, if we did not have an exception, so if we got a future, for example, as a return value, if we got a future out of the coroutine, then we want to schedule the step function again, and as soon as the future finished. So when this future finished, which represents something that we must wait on, then we can resume this task, remember? And when we resume the task, we want to go back here and do corout.send again. Continue, execute the coroutine again until it yields or until it finishes. So we do, this is kind of like we loop, the event loop loops between tasks. And every task loops between the step function for the coroutine until the coroutine has finished in some way or another. So that's a task. And remember from the earlier slide, we also had this handle. And the handle is also very important, because what the handle is a wrapper for a callback that we schedule inside the event loop. So we want to tell the event loop, okay, this is going to run inside, and we want this callback to run, okay? And we create a handle for that, so that it's not just thrown into event loop and we lose control over it. We create a handle for this, so we can then have some callback. We can have a callback. We can cancel the callback and stuff like that. So the handle is supposed to give us a handle on whatever we throw into the event loop. And in practice, what we're going to throw into the event loop is the step function. So we're going to schedule into the event loop the step function. Remember, we loop between tasks, we loop within a task, we loop between steps. So that's what we actually put inside our event loop. This also means that the handle is the main interface between AsyncIO and Qt, or whatever your event loop implementation is going to be. Because the handle is the point where we say post this event to the event loop, so that the event loop at some point will say, okay, I will run this. The handle is what allows us to do this. It's the main interface between these two worlds. So this is part of my handle implementation. We're not going to go into the detail here, just want to show you we've got this callback, and we do have some some management code inside, but eventually we're going to run the actual callback. And this function is what, in Qt's case, is the function that posts an event to the event loop. If you have your own implementation, that's going to be whatever you need. But this is basically what we are going to schedule inside the event loop, right? And we're going to call this callback. That, in our case, is the step function from the task. So we've covered futures, tasks, and handles, and that is already those are already the most important ones, apart from the event loop itself. The event loop is the bulk, the principal component of the AsyncIO API. It has functions in this API to run the loop until a feature is completed, to run it forever, or to stop the loop, close the loop, schedule a callback, create features and tasks, and in brackets this user-facing API that I'm not talking about here, but all this is part of the event loop API. So it's quite a bit. This minimap might give you an impression. This is my implementation, and it's still not finished. So AsyncIO has this pretty funny sentence in their documentation. They say, it declares very many methods. Implementing all of them from scratch is a tedious job. Well, emojis from me. Well, I can certainly confirm this. But in all fairness, they do warn you. So if you are insane enough to try this yourself, you have also been warned. It's white on black. Here there is some code from site event loop. I think we're a bit short on time, so I'll go through this very quick. What I only want to show here is run until complete, runs until a future is finished. This is a bit misleading because it does not have to be a future. Oh, you can barely see this, I'm sorry. It can be also a future-like object. So in the case of our initial coroutine, this will be like the task for our first coroutine. Remember, we got the coroutine, we create a task for this, and then we're going to run until this task for the initial coroutine is finished. And we also got callbacks when the future is done, or in this case the task, where we say we can stop the loop when we finish this coroutine. And we run the loop forever, basically. And in Qt's case, it looks like this. You might remember the exec function I mentioned earlier. That's how our event loop is actually going to start executing. And that's what we do here. If you have your implementation, that's going to be some other function. So there have been a few concepts in class here: futures, tasks, handles, event loops. And if you are like me, when I start doing this and reading about this, you might be confused. Because there are many objects. They interplay in several ways. It's a bit hard to understand. And curiously, or unfortunately, there is nothing like a clean diagram inside the documentation that tells you how they play together. You need to read documentation of future, then for tasks, try to understand how they play with each other. And this is a bit hard. So what I'm going to show you a diagram that I think maybe is actually going to help you to bring all these concepts together and understand what the heck is actually going on with all this. So I'm going to show you what happens when we run an asynchronous program starting with this initial coroutine. From start to finish, what are the steps? How are these objects involved? Okay. So the first thing we do, we've got the coroutine, and we call AsyncIO.run with this coroutine as its argument. For this coroutine, we created tasks. The task has the step function, implementation detail, and we've got a callback, part of the API. When this task finishes, the callback will stop the event loop. The task creates a handle for this coroutine. When we create a handle, we enqueue a callback into the event loop. At this point, the event loop is not yet running. But at this point, we can actually start our event loop. Okay? We've got this handle callback that we enqueued into the event loop. This callback is going to execute the task step function. Remember, we loop between tasks, we loop between step functions. So that's what our callback is going to execute. Inside this task step function, we're going to execute the coroutine. Remember, coro.send inside our task. We're going to execute the coroutine until it finishes or raises an exception or it returns a future. If a future was returned, the task is going to await the completion of this future, or maybe we get an exception. And while this task is waiting, the event loop switches to another task, the cooperative multitasking. So tasks can spawn other tasks. Eventually, at some point, all tasks except for the initial task will have finished. We come back to the initial task, and at some point, that is going to finish too. So we're going to run the event loop until this initial main coroutine is finished, which then finishes this task that we created for it. And this task callback is then going to stop the event loop. So this is how futures handles tasks, the event loop itself, and finally coroutines all interact together, how they play together. And it's maybe not, I'm not sure why they don't show you a diagram explaining it. They make it a bit hard on people than maybe they should. But I hope that this diagram maybe makes it a bit easy to understand. I know it did for me. Can you tell me 1 second how much time we have left? Okay, because I still have one slide I'm just going to show you. Otherwise, I would have skipped this slide. But if we have a moment more, I'm going to show this slide. There is one class that I had earlier when I had a list of these essential classes. One of them I did not explain it. It's the executor. So the idea of an executor is sometimes in our program we want to run a callable that's not a coroutine, and this might also be blocking as well. So maybe we want our program to handle these callables as if they were coroutines in a way. Like we want to await these, we don't want to block on them, and so we wonder, could we maybe await the result of this callable so that the entire program is not going to block waiting on this? And here we can cheat a little. We can bypass the single-threaded paradigm that I was talking about earlier by introducing threads. So the solution is this executor. The executor offloads this callable to a separate thread or process and awaits its result. So it's a bit cheating, but it works. And this callable is then run asynchronously. So that's the executor class. And now, if you try to do this yourself, or at least in my case, I found a pretty big complication. So I want to talk about the process as well, right? It's not just about the API or about the class. It's all about the process. The process for me right now is here, needing to handle this beautiful line from the documentation. Executor must be instance of thread pool executor. You could create your own executor class before, and now you can't. And unfortunately, this creates big problems with Qt because when we create a separate Python thread, we do not have a Qt event loop anymore. I'm going to go into the details here for lack of time, but the point is it's not always straightforward. This is also not finished. This is kind of work in progress. So right now, this is what I'm grappling with, and I would really like to know why they actually changed this. So this is what I'm right now in the process of figuring out. So things are not always clean. They're not always straightforward. It's a process, and in due fairness, they do warn you, but I've learned more about asynchronous programming than I ever have before in my life with all this. And perhaps you would too if you do this yourself. So just, this is a very simple, maybe stupid demo, but this is just, at this point, it's very hard to see. Well, you can see this is the C of Eratosthenes, which this algorithm for calculating prime numbers. This is done with AsyncIO. This is of course not a practical example because why would we do this? It's kind of like it has artificial delays with async, like with async.sleep, AsyncIO.sleep. It's an artificial example, but it just shows that all this infrastructure works. So it's kind of just supposed to highlight that. That's the example I'm currently running with. And so this runs with AsyncIO with my event loop. It's a transparent replacement. If you run this with AsyncIO itself, it's going to look exactly the same. It's not going to work the same because this actually uses like Qt classes for a user interface. Sorry, that was thinking of another example. This uses Qt code for the user interface based on AsyncIO. So there's an AsyncIO program, but you use Qt widgets and Qt main window and all that stuff. So then the idea becomes, it's as simple as this. You import the event loop policy, you set the event loop policy, which basically just tells AsyncIO what our event loop class is. If you do your own stuff, then this is how you transparently replace the event loop. It's very simple. And PySide, as I said, also showed earlier, you can just get through simple pip install. And you'll also have a bit of this AsyncIO code on there already, with more to come. And this is my email address, in case anyone wants to know more about this. And yeah, I think that would be it. So yeah, thank you for your attention. I hope I didn't lose you somewhere along the way. Maybe we can leave the presentation on this diagram for the Q&A. So yeah, thank you for your attention.
All right, thanks a lot, Adrian. That was great. Right, do you have any questions? Please raise your hand. Okay, over there.
Hello. First of all, thank you for your speech. For me, it's a little complex stuff. I don't know if you talked before, but imagine you have a plain script with a lot of synchronous function, and for whatever reason you need to create an asynchronous function. The function that call that asynchronous function will be asynchronous as well. So is there any way of abstract synchronous from asynchronous? Or it's
I'm not entirely sure I understood your question, but the thing is, if you want to write a synchronous program, you need to kind of get into the mindset that it's a different paradigm. So you want to write an asynchronous program. if you want to write a synchronous program and have some asynchronous function somewhere, that's, I think, not really how you would really do it. You would more approach the program from the start thinking it's a synchronous program where we have coroutines. And so you would do it like that. I mean, in principle, you could, of course, just have a synchronous program and then inside you just run, you do AsyncIO.run for this one coroutine. If that's the only coroutine you have, might be a bit of unnecessary overhead at that point. Depending what your program is, might be a better idea to just create a separate thread. It's more like if you might, I think you would rather say from the beginning, this is going to be asynchronous program. You get into the mindset, the paradigm, and then you work with coroutines. If you just have one coroutine, might not really be worth it to do the event loop only for that. But I think that might depend on the use case. Maybe if you got it's one coroutine, but it's like something that does a lot for this program, like I said, the server. Let's say you have, the server has a ton of synchronous code first, but then at some point we run this coroutine. We only have this one coroutine, but that's like the entire server. And it's just one coroutine, but it's a big part of the functionality. I think in that case, maybe it might make sense to do it like that, yeah.
Okay, thank you very much.
Sure.
Hi, thank you for your presentation. I was wondering that in C++ we have public slots, but also private slots. Do we have private slots in Python as well?
Well, in Python, you don't really have private and public in that sense, right? So, I mean, if you talk about Qt specifically now, I mean, a slot is simply going to be some field of an object, and it's just going to be, well, basically public. And we don't really have public and private in Python, right? I mean, we have through convention, we might have an underscore indicator it's supposed to be private, but we don't really have that form of, we don't really have that in Python. But maybe I'm not quite sure I understood your question.
It's about just the definition that we have in C++ that we can like use the private slots to avoid the ABI, the binary compatibility, to ensure the binary compatibility. But I guess here in Python there is not such problem, so it's not needed.
Maybe come back to me after the Q&A, because I'm not sure I understood your question, but I want to discuss this. Okay. Maybe, I mean, unless there are no other questions, of course, then, but.
Yeah, thank you.
Okay, any other questions? Anything else?
Doesn't seem like it.
Okay, in that case, that will be a wrap. Please, big ovation once again for Adrian. Great work.